Hey guys, welcome back. So we're going to start off with some board questions from yesterday's lesson. So because you can pause these videos, I'll just let you pause it now if you want to try it on your own, and then I will go through it. Okay. So this first question here is asking the correct free body diagram for a frictionless block. So if it's frictionless and it's just a block sitting on there, there's going to be no friction, there's going to be no force applied. So all that we're going to have is a force of gravity, which all of these have, right? Force of gravity, force of gravity, force of gravity. And that force of gravity has a dot that line, a force of gravity parallel, and a force of gravity, that's force of gravity perpendicular, and a force of gravity parallel. So all of them have that. You can break it up and you cannot break it up. It doesn't need to be broken up on there. But the only other force is going to be a force normal upwards like that, right? It's not going to have any of these forces off to the side because it's that parallel component that's going to cause that block to slide down there. Okay, so A is the correct answer. For the second one, it's a calculation. So a cement block has a mass of 20 kilograms. It's at rest on an inclined plane. So it being at rest is an important thing because it tells you that the forces are equal. So what is the normal force acting on the block? So we got this Fg. Again, we can break it into our perpendicular component, and we can break it into our parallel component. Remember that these should always be a 90-degree angle here. And then we have our normal, which is perpendicular to the surface. And it's at rest, so there's some friction that's keeping it up. And I'm going to move this force of gravity parallel so that it's here. So this question is asking what is the normal force. So what a lot of people will do in this question is they'll say that force normal is equal to force of gravity, right? And they'll just say, oh, well, force of gravity equals mg, so 20 kilograms times 9.81 meters per second squared. And they'll say, okay, 196. So that's wrong. That's not what you want to do. So because remember that when you're on an incline, force normal doesn't equal force gravity. It equals this force of gravity perpendicular. So Fg is still mg, it breaks down, but this perpendicular always breaks down into cos. So we would go cos of our angle, which is 30 degrees. So 20 times 9.81 times cos 30 here, and that would give us 170. So it's not straight up. It's always going to be perpendicular to the surface, which makes D the correct answer. Okay, and this last one, Ben and Jill are on a tandem bike and start to accelerate down the ramp with a slope of 30 degrees to the horizontal. The two people on the bike have a combined mass of 130 and the frictional force acting on the wheels is 83. The acceleration the bike will have down the hill. Okay, so it looks like they're just coasting down the hill. So I'm going to switch to my camera view for this one. Okay. And so we'll draw on that free body diagram. There. This is 30 degrees. They have a mass of 130. We have our force of gravity, which is straight down. We have our perpendicular and our parallel component. And always just throw your parallel component on there. So that parallel component is what's causing them to go down the hill. There's a force of friction. It's accelerating down the hill, so that force of friction is going to be up the hill, and it's going to be smaller. It gives our force of friction 83 newtons. And then we have our force normal like that. Okay. So we're looking for acceleration, the direction of motion. So that's going to be these two forces here for our F net equation. So F net is going to be equal to Fg parallel minus my force of friction. This is mass times acceleration. Fg is mg, line is sine, and force of friction we don't have to break down because we know it. So we move our mass under here, and we're ready to answer the question. So it's 130 kilograms times 9.81 times the sine of 30 degrees, and our force of friction is 83 newtons, and it all gets divided by our mass of 130 kilograms. So we're ready to type that in. So 130 times 9.81 times sine of 30, all in brackets, minus 83, that's my top, all divided by 130, and I get to 2 sig digs, I get 4.3, so that means that C is the correct answer for this one. Okay, so I hope that went well, and if you have any questions about that, just let me know. So today we're going to be learning a lesson about vectors at non-right angles. Just getting everything ready to go. Okay, let's learn about this. So sometimes when you add two vectors that are not, sometimes you may have to add two vectors that are not going straight east-west or north-south, right? Everything we've been doing so far is so-and-so walks that way, so-and-so walks that way. What is their displacement, right? So-and-so walks north, so-and-so walks east. What is their displacement, right? Everything's at these nice right angle triangles. So what we're going to learn about today is what happens when you're not at a right angle triangle. So you can still use tip-to-tail vector addition to find your resultant vector, but the problem is you don't get a right angle triangle. So here's an example here. So we have two vectors, and if we add these tip to tail, there we go, throw some flare into there, and we draw on our resultant vector like that, you can see that this does not give us a right angle triangle, right? So we can't use SOHCAHTOA with this, and we have some problems, so we're going to learn how to do these types of questions. So how does all solve a vector problem? So your first step is to break it into X and Y components, which we've already kind of done with the lawnmower questions. We break it into X and Y, and also with the inclined plane questions, we were breaking into parallel and perpendicular, which is pretty much the same thing. Okay, so I'm going to start off by drawing these out. So we have two vectors here. We have this vector, which is 15 meters per second, and it's 75 degrees south of west, so I'm not going west, I'm going 75 degrees south of west. So the 75 would go into here, and our length is 15 meters per second. So you can see with this, we have an X component, and we have a Y component, like that. So that's one of our triangles. And our other triangle, we have, looks like this. So it's going to be a little bit longer than that because this one's 15, so I have to make this one 35. And we're not going south, we're going east of south. So that's nice and straight. So our angle is 10 degrees, and we have this Y component, and we have this X component. Okay, so those are our two triangles, and we have a side, we have an angle, so we can use SOHCAHTOA, and we can figure out what those unknown sides are. So to find X, we have adjacent and we have hypotenuse. So I'm going to set it up. Cos of 75 degrees is equal to adjacent, which is my X, over my hypotenuse, which is 15 meters per second. Move that 15 meters per second up there. And that's how I would find my x component. For my y component, it's going to be opposite and hypotenuse, which is sine. So sine of 75 degrees equals opposite, which is y, over hypotenuse, which is 15 meters per second. And this is 15 meters per second. And I move that up there. So if I want to find my x component here, I just have to go 15 cos 75, and I get 3.88 meters per second. And then my y, I just have to go 15 sine 75, and I get 14.49. You're not supposed to round, but I'm going to show you why I'm rounding later. Okay, with this one, we have adjacent. Oh, I forgot to fill in this side here. So this is 35 meters per second. So for y, we have adjacent and hypotenuse, which is cos. So cos of 10 degrees is equal to adjacent, which is our y, over 35 meters per second. So move that 35 meters per second up there. And for our x, it's going to be opposite over hypotenuse, which is sine of 10 degrees. And that's going to be our x over our hypotenuse. So move the 35 meters per second over here. So now I'm ready to type that in. 35 cos 10 gives me 34.47, and then 35 sine of 10 gives me 6.08 meters per second. So I broke it all into x and y components, and that is our very first step. So our next step in doing this is to add positive and negative signs. So when doing these questions, you can make everything going up positive, and to the right positive, and down negative, and to the left negative. So you can see this x is going to the left here, so we're going to make this negative. The y is going down, so we're going to make this negative. Here the y is going down, so we'll make this negative, and my x is going to the right, so I'll make it positive, just following those coordinates. So 3 of them are negative, and 1 of them is positive. So our next step is add together your x and y components. So we're going to want to add together all our x's, and we want to add together all our y's. So now what I'm going to do is I'm going to take my x, which is negative 3.88, and I'm going to add it to my other x, which is positive 6.08. So I'm going to add negative 3.88 with 6.08 positive, and I end up getting 2.2 meters per second. These are all meters per second. And then I'm going to add my two y's together. So negative 14.49, and I'm going to add it to negative 34.47. So with that, I get negative 14.49. I'm going to add it to negative 34.47. And I get negative 48.96 meters per second. So this is my total x, and this is my total y. Okay, this is positive. So to show you why we do this, I have a little animation here that I made. So these are two original vectors, and then this is my resultant vector. So what we did first is we found the x component of our one and the x component of the other. And then what we did is we added them together. One is to the right and is bigger, one is to the left and is smaller. So when we add those together, this is what we're left with. Okay, so we're just going to make that go away for a sec. And then we found our y component from one and our y component from the other. You can see that they both go downwards, so they add together. So what we end up getting is a bigger y component. So now I'm going to bring back the x component from before, and I'm going to add them together tip to tail, and you can see that this is the same resultant for this tip to tail, only now we have a right angle triangle to work with. So our next step is to make a new triangle based on the total x and the total y. So I'm going to go back to my drawing here. So my next step is to draw this triangle. So it's positive, and we said positive goes to the right. So I'm going to go to the right 2.2 meters per second. And this one's negative, and negative means that we go downwards. So I'm going to draw this as negative 48.96 meters per second. And this is my resultant, right? This is my total. That's what I'm trying to find. So our last step is solve using tan -1 in Pythagoras, and it's always going to be the same. So to find this resultant, I can go 2.2 meters per second squared plus 48.96 meters per second squared. And you can see I got rid of this negative. This negative just tells us we're moving down. Get rid of any negatives or positives after that. It's just going to make it a little bit harder to calculate. So 2.2 squared plus 48.96 squared. Oops. I typed an extra decimal place. So 2.2 squared plus 48.96 squared. And we square root our answer, and we end up getting 49.0 meters per second. And then we can find this angle here. Remember, we find the angle with no arrows on it. And we have opposite and adjacent, so we want to use tan -1 of opposite 48.96 over adjacent 2.2, and we type that in. And we end up getting 87 degrees. And this angle here, we're not going east, we're going south of east. Right? If you drew it the other way around, 3 degrees east of south would also be an acceptable answer. So this is our final answer, and that's how we do it, and that is a ton of work. So this was a hard way of doing this. Now I'm going to show you an easier way of doing this. There's a lot of places to make mistakes in there, and I want to make things easier for you. So I have another technique of solving this question, and it's called the RCS technique. So RCS is a system that allows you to solve problems like the last one with minimal thinking and minimal mistakes. There's just a couple rules that you have to follow. To use the RCS technique, all angles must be in RCS form. And you probably forgot what RCS form is, but I'll do a little bit of review of that when we're doing this question. Y components are always sine, and your x components are always cos. So I have a fun little way of remembering that. Much like FG line is sine, all you have to remember is y is sine, y is sine, and you can put this on a loop and you can listen to this all day because it's a recording. You can just know that y is sine, y sine, y sine, y sine, and x is cos. Okay, so use that y sine to help you remember, and you're always going to add any numbers that you get. Okay, so those are our rules when using the RCS technique. So what we're going to do is we're going to solve the exact same question that we just solved, but we're going to use the RCS technique this time. Okay, so I'm going to go back. I'm going to erase all of this right here. And I'm going to leave this down here because I'm going to show you that we get the same answer. We don't need as much space to work. So for this question, we're going to build a little chart here. So this is x, and this is y, and this is vector 1, vector 2, and this is our total. So to keep things organized, we do a nice little chart like this. So what we need in here is we need a magnitude. So vector 1 is 15 meters per second, and this is and vector 2 is 35 meters per second. Okay, and the next thing that we're going to do is we're going to figure out what our angles are in RCS. So our first angle is 75 degrees south of west. So I'm not going west, I'm going 75 degrees south of west. And then remember that RCS zeros over here, 90, 180, and 270. So we're going to go 90 plus 180 plus another 75. So 180 plus another 75 gives us an angle of 255 degrees. And we'll do the same thing for our other angle. We have north, east, south, and west. And our next angle is 10 degrees east, south. So we're not going south, we're going 10 degrees east of south. So this is 0, this is 90, this is 180, and this is 270. So 0, 90, 180, 270 plus another 10. So this one is 280 degrees. And that's the hardest part of this, is just getting all those angles correctly. So what we do is we do magnitude, 15, and then x is cos, and then our angle in RCS. So 15 cos 255. Same thing here, our magnitude is 35 cos, and our angle is 280. This one's going to be magnitude, but y is sine, and then our angle, which is 255 degrees, and then magnitude 35 meters per second, sine, and then 255 degrees. Oops, sorry. 280 degrees. Okay. And now I'm ready to type that into my calculator. So what I want to do to find my total is I just want to add these two numbers together. So I'm going to go 15 cos 255, close my bracket. You can kind of see that in my calculator. And then I'm going to add it to 35 cos 280. Make sure you're in degree mode, and we end up getting 2.195 meters per second. And then a little trick here is if you push second enter, it'll type in the same thing that you just typed in. And the only difference between the x and the y is our y's are sine. So I just go over to cos and switch it to sine. And I go over to cos, switch it to sine. And I end up getting negative 48.957. And that's meters per second. So we look at this answer, 2.195, 2.2. 48.957, right? They're a little bit different because, well, I rounded these, but they're still spot on, right? To 2 sig digs, this is correct. To 2 numbers after the decimal place, this is correct. This is a lot easier. This is the way that you want to do it, right? And then to finish off the questions, the same as before. So x is positive. So positive means we go to the right, 2.2. We go down, 48.957 meters per second. So this is 2.195 meters per second. And we find our resultant. So we just do all the same stuff. The work's going to be the same. We're going to Pythagoras, we're going to tan -1, and we get the same answer. Just a lot less work in that first step. Okay, so I'm going to do another question here that was originally a board question, but we can't do board questions like this. So I'm going to do this question for you. Feel free to pause the video and try it yourself and see if you can do it, and then watch me go through it after to see if you get the same answer. Okay, so a lynx is walking 500 meters 12 degrees south of west towards a small stream, then walks 1200 meters 45 degrees north of west back to the stream. Then the lynx walks 0.3 kilometers straight east. Find the lynx total displacement. Okay, so the only difference between this question is I'm going to do, oh, I'm not on my camera. I'm going to do a little bit of a bigger RCS chart because instead of just having 2 vectors, we have 3 vectors. This is X, this is Y, and this is vector 1, vector 2, vector 3, and this is our total here. So the biggest place that people make mistakes is switching the angles to RCS. You got to remember to do that. So you need a magnitude. So vector 1 is 500 meters, and we need an angle. So just draw them out like this: northeast, southwest. And it says that the angle is 12 degrees south of west. So I'm not going west, I'm going 12 degrees south of west. And this is 0 degrees, 90 degrees, 180 degrees. So it's going to be 90, 180 plus another 12. So 180 plus another 12 is 192 degrees. Okay, and I'll do the same thing with the next vector. So it says that the link sin walks 1,200 meters and goes 45 degrees north of west. So I'm not going west, I'm going 45 degrees north of west. And this is also 45 degrees. So I'm going 90 plus another 45. This is 135 degrees. And then my last one, the lynx walks straight east. So straight east is going to be this way. Straight east is 0 degrees. So the angle is 0 degrees, and it gives the distance as 0.3 kilometers, but we have to, if this is meters, this is meters, then we want this one to be in meters. So we're going to go 300 meters instead of 0.3 kilometers. Okay. So magnitude, 500. X is cos, 192. Magnitude, 1200. Cos, 135. Magnitude, 300. Cos, angle, 0 degrees. Same thing here. 500 sine 192. 1200 sine 135. And 300 sine of 0. I'm going to take those. I'm going to add those numbers up. 500 cos 192. Close my bracket. Add it to 1200 cos 135. Close my bracket. Add it to 300 cos of 0. And we should get negative 1037.6. And these are all distances, so that's going to be meters. And then that little trick, I push second enter. And I switch all of my coses to sines. Cos to sine. And cos to sine. And I get positive 744.57 meters. Okay. So remember that up and to the right are positive, down and to the left is negative. So my x is negative. So I want to draw it as 1037.6, and I want to draw it to the left because it's negative. Oops. This one's positive, so I'm just going to switch this. So 744.57, so it's going to go up. And remember, don't have any positives or negatives on there. It's just going to throw you off in the long run. Okay, so this is our total displacement. So we have to go 1037.6 meters squared plus 744.5 meters squared, and then square root it. So I have those answers in there already. So I'm just going to delete the negative from there. And I'm using my full answer like a good person. And then square root my answer. And I get 1277 meters. And I also need an angle. So I find my angle where there's no arrows. And it's going to be tan negative 1 of opposite over adjacent. So 744.5. over 1037.6. Okay, so I tan negative 1, and I'm going to grab my answers from before, divided by 1037. I'm going to get rid of the negative in my calculator because that's going to throw me off. And I get, how many sig digs? We have 2 sig digs. 36 degrees. I'm not going west, I'm going north of west, right? And the other answer that works is if you did 54 degrees west of north, if you drew it the other way around. And this should be to 2 sig digs, but whatever. Okay. So hopefully that made sense, and hopefully you can try some of the homework with that. We got a couple more things left to do before we call it a day, I think. Oh yes, this comet question. So, yeah, I'm going to throw in a little video here where this is where I got the idea from the comet question from, and it talks about different ways that the world could end. And one of the ways is a comet hitting the Earth. So I'll show you that video, and yeah, that is all.
Comets. If you thought asteroids were bad, wait until you get a load of what might happen if one of these comes our way. By now we know that asteroids can really pack a punch, and if we need to stop one that's headed for us, we're going to have to know as much about it as possible. But what if the object approaching us turns out not to be an asteroid at all? What if I told you that there was something even more dangerous out there than asteroids? Something bigger, faster, something we don't know where to look for, and that can change direction on a whim? Well, that something is a comet. A comet is basically a collection of debris frozen together into a big ball of cosmic ice. And that ice makes a comet's movement unpredictable and deadly. And I can mimic that with a ping pong ball. All I have to do is poke a hole in it, and then another one this way. Fill it with liquid nitrogen, which is at 300 degrees below 0 Fahrenheit. Now you can see the jets coming out here and here, and in a comet, that's what really happens. When this thing gets near the sun, that ice turns back into a gas and forces its way out. And then when you watch the comet, it starts rolling around in all these crazy directions depending on which way those jets are pointed. And we can have a comet pass very close to the Earth and miss us, except to have a jet suddenly push it into us. And that's what makes comets even more dangerous than asteroids. Remember back in 1997 when the comet Hale-Bopp streaked across our skies? Well, that comet was discovered less than 2 years before it passed near us. And moving at 70,000 miles per hour, if this 25-mile wide comet had changed direction and headed our way, well, we wouldn't be here talking about it right now. So now that I've scared you, comes the next question. Is there anything we can do to stop a comet? Well, to find that out, we're going to need to make a comet. And I've got everything I need to do that right here. So this is going to be a pretty good approximation. Water is the main ingredient of comets. I'll put in a spritz of ammonia, a very common ingredient in space. Corn syrup, which will be our organics. There are various organic compounds found in comets like amino acids, the building blocks of life. Some dirt, because there's lots of rocks in comets and it has carbon in it. So here comes the charcoal. Comets are cold, and so I need to chill this with dry ice. There is frozen carbon dioxide in comets, so this is not entirely unrealistic. So I'll just shake that up a little bit, and as the dry ice goes from being a solid into a gas, now let us see what we've made here. And we've got a comet. So now that we've got our little scale model comet, how can we use it to figure out how to stop one of these things? Well, comets are made of ice, right? So if you're thinking heat, you're on the right track. Remember, comets change direction by venting gas. So could we use the heat from a laser to drill a hole in the comet, making it shoot out enough gas to change direction? Well, I just happen to have something here that might tell us if that'll work. Check this out. Oh! Watch this. Whew! That's hot. So we have our comet, and we have our heat source. Now let's see if this theory holds water, or in this case, gas. If this works, the heat from our laser will cause our model comet to emit a small amount of carbon dioxide. It's doing something. We are seeing a little bit of outgassing. But could these little jets of gas create enough push to change the direction of our comet? All right, let's go. Well, let's pretend our model comet is the real thing and see if we'd be able to save Sydney from Comet Armageddon. Oh well, so long, Sydney. So we're gonna have to find something.
So now we're ready to finish off this question. After watching that video, Sydney got destroyed. Shoot, the city, not the student. Okay. So a comet is traveling at a velocity of 3,000 meters per second west through space, which is kind of stupid because there's no west in space, but we'll keep with the 2D stuff. All of a sudden, 4 plumes of gas eject off the comet at the same time. So we're going to draw a free body diagram of the comet. Okay, so let's draw that out. Erase all this. So this comet has those plumes of smoke coming off. And remember, with a rocket, it's always Newton's third law, equal and opposite. So there's a plume of smoke that's going down, but that's going to cause a force upwards. So it's going to be a force upwards of 30 kilonewtons. Okay. And then there's a plume of smoke going this way, so that's going to force the rocket this way, and that is also 30 kilonewtons at an angle of 30 degrees, everything 30. And then there's a plume of smoke going this way, and that's going to push it this way, and this one's a larger one. This is 35 kilonewtons. And then there's a plume of smoke going this way, so it's going to force it that way, so it's 10 kilonewtons, like that. So that's our free body diagram. So the next part of the question is asking us draw a tip-to-tail vector addition showing the net force on the comet. So with the other questions that we were doing, we always started where we finished with sign questions, and there's always 3. But with this one, there could be a net force, so we probably won't start where we finish. So it doesn't matter which one you start with. So I'm going to start with this one here with 35 kilonewtons. And I'm going to add this one tip-to-tail, so the 30 kilonewtons is going straight up, and I'm going to try to make it a little bit smaller than the 35. And then I have 10 kilonewtons going that way, and then my last one is 30 kilonewtons like that, going at an angle of 30 degrees. So my resultant is going to be this. Oh shoot, I forgot to switch my camera, sorry. So I drew my 35, and then my 30, and then my 10, and then my 30. So this is my resultant force acting on it. So you can see that we can't use SOHCAHTOA to figure this out, and that's when you use an RCS chart. Whenever you don't get a right angle triangle, this is not a right angle triangle, you use an RCS chart. So that's what we're going to do to finish off this question. So we're going to draw an RCS chart because the last part of the question is asking what will be the magnitude of the net force. Well, let's use an RCS chart, and this time I'll switch my camera. So this time, make it a little bit bigger. We have 4 vectors. So 1, 2, 3, 4, like that. We have x, we have y, so vector 1, vector 2, vector 3, and vector 4, and this is our total. So I'll just do it in this order. And the angles are pretty easy because we have to make those angles in RCS, but this is 0, 90, 180, and 270 degrees. So this one's going straight east. So this is going to be 35 kilonewtons. We can keep it in kilonewtons as long as they're all the same. And it's going straight east, so this is going to be 0 degrees. And then this one here has 30 kilonewtons. And it's going straight up, so that's going to be 90 degrees. This one is 10 kilonewtons, and it's going straight west, so that's going to be 180 degrees. And then this one, so this would be 270 degrees down here, plus another 30. So we have 30 kilonewtons, and it's going to be 300 degrees because it's 270 plus a 30. So we can fill out our RCS chart. 35 cos 0, 30 cos 90, 10 cos 180, and 30 cos 300. And same thing for the y, 35 sine of 0, 30 sine of 90, 10 sine of 180, and 30 sine 300. So now we're ready to type those in. We'll add up all the x's, 35 cos 0, plus 30 cos 90, plus 10 cos 180, and 30 cos 300. Right, I just add them all up in one. We get 40 kilonewtons positive. Push second enter, switch all my coses to sines, sine, sine, and sine. And I end up getting 4.019 kilonewtons, also positive. Okay, so, sorry guys, if there's a little blip there, I got a phone call and I record the audio on my phone, so yeah, shut off my recording there. So let's finish off this question. So now we have our total x and we have our total y, so we can draw on our 40. It's positive, so we go to the right. And this is positive 4, so we go up. So 4.019 kilonewtons. And then this arrow here is going to be our net force. And if we take a look at this drawing here, and our original drawing there, right? This is our net force, this is our net force. It looks the same, but now it's a right angle triangle, so we can use Pythagoras and tan -1. So we have 40 kilonewtons squared plus 4.019 kilonewtons squared. And we square root it. So to do that, I have my numbers in there. So I'll just grab them, 40 squared plus 4.019 squared. And I'll square root my answer. And I end up getting 40.2 kilonewtons. And then I need my angle. So to get my angle, I'm going to tan -1 of opposite over adjacent, and when I do that, tan -1 opposite over adjacent, and I get 5.74 degrees. I'm not going east, I'm going north of east. There we go. And that's how you solve that question. So there's one more question here that we'll take a look at, and then we're all done after that. Let me get this opened up. Oops. Oh, I gotta delete these. There we go. Sorry, everything's screwed up when that phone call happened. So let's get this up. So the last question will be, describe what will happen to the motion of the comet over time. Okay. So what that means, so originally it was traveling west through space. So let me open up this again. So it's traveling west through space, so it's going this way, and then all of a sudden it experiences this total x and this total y force. So what's going to happen in the x is if it's traveling this way and experiences a force this way, it's going to slow down, slow down, slow down, stop, and then it's going to go that way, all while experiencing this force upward in the x. So if we combine those together, it's going to be moving west, slowing down, stop, while moving up. It's going to travel in a path that looks like that. Okay. So that's RCS chart questions. That's how you do them. And these are your homework questions. So make sure you try them. There's not very many. There's 7. Make sure you are in degree mode. Make sure you're converting those angles to RCS. And email me or comment or whatever you're going to do to get a hold of me if you're having trouble. And I will help you with it. So thanks for listening. And that is it.